Section 10.8 is Taylor and Maclaurin series. If you'll recall what the power series looked like from section 10.7, you're going to see some similarities between the power series and the Taylor and Maclaurin series. Just in case you've forgotten, this is what the power series looks like, where these are going to be the constant terms, and this will be your variable for the polynomial that you generate from this infinite power series. And then last time we looked at how to find the domain of the power series by determining what the interval of convergence was. For this power series, where would we say that this power series was centered? This one's centered at x equals 0 because we don't have x minus a number in parentheses that's being raised to a power. This first definition is that of a Taylor series that's generated by a function at x equals a. So we're going to let f be a function with derivatives of all orders throughout some interval containing a as an interior point. A is where this series will be centered because we see this x minus a right here. Now notice these constant terms from the power series, they're going to be determined for a Taylor series by this part of the series. And then we have x minus a raised to a k, just like we had our variable part of our power series from last time, x raised to a power of n, we've got x raised to a power of n. So the Taylor series tells us how we can determine what those constant terms are going to be. So the Taylor series is going to be the sum k equals 0 to infinity of the kth derivative evaluated at a divided by k factorial. Here k would be the index of our power series. When I write the series, I typically choose to use an n as the index for my series. But you can use any variable. There's nothing special about k's or n's. So if we were to expand this out, the first term we would get when k is equal to 0, and when you raise anything to a power of 0, you just get 1. The 0 derivative is just the function, so that's why this first term right here is just f of a. And then to get the second term, that's when k is equal to 1, that would be the first derivative evaluated at a times x minus a to the first. The third term would be what you get when k is equal to 2, and that would be the second derivative evaluated at a divided by 2 factorial. We're going to use this term right here to determine the constants in front of x minus a raised to a power. The Maclaurin series is simply a Taylor series centered at 0. So once you memorize the form for the Taylor series, you can get the Maclaurin series. So the Maclaurin series is just a Taylor series that's centered at 0. That's why whenever we're working with problems, we typically write down the Taylor series. If we let f be a function with derivatives of order k for k equals 1 through some finite number n, in some interval containing a as an interior point, then for any integer n from 0 up to that upper bound n, the Taylor polynomial of order n generated by f at x equals a is a polynomial. And we use a subscript of n here on the Taylor polynomial to determine where we stopped. What's the highest power we're going to go to for x? The series goes from 0 to infinity, but the polynomial has a stopping point. It's going to be a finite number of terms from the Taylor series. I believe in section 10.7 we looked at a power series for e to the x, and I told you that the power series for e to the x was just the series of x raised to the n divided by n factorial. This graph to the right shows the graph of f of x equals e to the x. That's this graph right here in blue. And then we see the Taylor polynomials, which is what we would get if we started with the first degree polynomial, which is a linear equation. P sub 1 would be 1 plus x. P sub 2 is 1 plus x squared divided by 2 factorial. That's this function right here. And then P sub 3 would be this gold graph right here. And you can see as the degree of the Taylor polynomial increases, this graph gets closer and closer. It becomes a better and better approximation of the graph of e to the x. And that's why we use Taylor polynomials, is to approximate a transcendental function using a polynomial expression. In example 1, we're asked to find the Taylor series for f of x equals e to the x centered at x equals 1. In the previous example, the Taylor series was centered at 0. I'm going to start by writing down what the Taylor polynomial is. This is the Taylor series formula. It says it's the series that goes from n equals 0 to infinity of the nth derivative evaluated at a divided by n factorial over x minus a to the n. When we're asked to find the Taylor series for a function, we start by finding the derivatives. Our function here is f of x equals e to the x. When n is equal to 0, that's just the function, f of x equals e to the x. When n is equal to 1, we're going to look at the first derivative, and the derivative of e to the x is still e to the x. The second derivative is also going to be e to the x. The third derivative will also be e to the x. And if I go on down, I can represent the nth term as the nth derivative evaluated at x equals e to the x. Now what I'm doing is I'm trying to get this part of the Taylor series. This is going to tell me what my constants are. Well, that tells me that I need to plug in an a in place of x. And for this problem, a is where we're centered, so a is going to be equal to 1. And e raised to a power of 1 is going to be equal to e. We're going to use these constants to find our Taylor series. Since every single one of these constants is going to be equal to e, the way that I can write my Taylor series is it's going to be the sum n equals 0 to infinity of e divided by n factorial x minus 1 raised to a power of n. If I were to expand this out, when n is equal to 0, that would give us e, and when n is equal to 1, e divided by 1 factorial is e times x minus 1. When n is equal to 2, we get e over 2 factorial times x minus 1 squared, and so forth and so on. This is what we get when n is equal to 0, when n is equal to 1, when n is equal to 2. I didn't have to show all of this work because we recognize right away that the constants here were going to be e. Once you are able to recognize a pattern, you can stop expanding these terms. In example 2, we're asked to find the Taylor series for f of x equals cosine x centered at x equals 0. I'm just going to keep writing this pattern down until I have it memorized. This is the pattern for the Taylor series, and this is what we're going to work off of. So we start by writing down our function. So we get f of x equals cosine x. That's our function. That's the function that we're going to use when n is equal to 0. When n is equal to 1, we're going to look at the first derivative, and the derivative of cosine x is negative sine x. When n is equal to 2, we look at the second derivative, and that's going to give us negative cosine x. When n is equal to 3, we have the third derivative, and that's going to give us sine x. And when n is equal to 4, the fourth derivative is going to give us cosine x. And then what we see is this pattern is going to repeat. So when n is equal to 5, we're going to get negative sine x when n is equal to 6. So I could just write these numbers down here, 5, 6, 7, and 8, and that pattern would repeat. So I've got a whole bunch of constants here. Now I need to evaluate the function at 0 for each of these terms. So f of 0 is going to be cosine 0, and cosine 0 is 1. F prime of 0 is negative sine 0, and sine of 0 is 0. F double prime of 0 is going to be equal to negative cosine 0, and that's going to be equal to negative 1. F triple prime of 0 is going to be equal to sine of 0, and sine of 0 is equal to 0. And then the fourth derivative evaluated at 0 is going to get us back to cosine 0, which is equal to 1. So I'm going to use these constants in this formula to plug in place of this term right here. Now, how I'm going to figure out what the series is, this one's a little more challenging than the last one was. I'm going to start by writing out a whole bunch of terms and look for a pattern here that will help me figure out how I'm going to write my series. So starting out when n is equal to 0, the constant term right here is 1. So that's going to give us 1 divided by 0 factorial times x minus 0, which is just x raised to a power of 0. Plus, for the second term, when n is equal to 1, we're going to get 0 divided by 1 factorial times x to the first. Plus, the next term is going to be negative 1 divided by 2 factorial times x raised to the second. Plus, the next constant we get is 0, so that's 0 divided by 3 factorial x to the third, plus the next constant then is going to be 1 divided by 4 factorial x to the fourth, plus after the 1 we go back to 0 divided by 5 factorial x to the fifth, plus after the 0 we're going to get negative 1 divided by 6 factorial x to the sixth. And this pattern will continue on and on and on. Now, these are the terms that I got when I used the constants over here based on what these values values of n were. So this was n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and n equals 6. Let's simplify this. Some of these things are going to go away, aren't they? This first term here is going to be 1. This next term is 0. Then we get minus 1/2 x squared plus 0 plus, we're going to call this 4 factorial, x to the 4th plus 0 plus negative 1 over 6 factorial, x to the 6th. What would the next term be if I were going to continue this out? It would be 0. And then I would have a plus 1 over 8 factorial. So all of these terms that are 0, I don't want them showing up in my series. They can't show up. And I need to figure out how I'm going to write this where this is the term, I get the 1 when n is equal to 0. And I get this when n is equal to 1. And I get this when n is equal to 2. And I get this term when n is equal to 3. Well, let's look at how we can do that. The 0 is easy. That's just 0. We skip the term that we had when n was equal to 1. And here, I need this, if I'm using the pattern, to be n equals 2. Well, that's going to be 2 times 1. And in the green above right here, this is the term that I got when n is equal to 4. But 4 is 2 times 2. And this is the term that I got when n was equal to 6. Well, 6 is 2 times 3. Do you see a pattern that I can use to write my series so that I have n being these numbers that are in red? So cosine x is going to be equal to the series that goes from n equals 0 to infinity of, my constant is going to oscillate. It's going to be a positive, negative, positive, negative. So I need negative 1 raised to a power of n because I want the first term to be positive, and when n is equal to 0, that will be positive. Now, how can I write this factorial down here so that I end up with the right numbers? I need this to be 2. I'm going to replace this n factorial with 2n because what I'm doing is I'm doubling these numbers to get this 2 right here and the 4 right here when n is equal to 2, and when n is equal to 3, I need this to be a 6. So the way that I do it is I double the numbers that I'm plugging in from the index on my series. And then this would be x raised to the 2n. That way, whenever I start with n equals 0, I do get this first term right here. When n is equal to 1, I do get this second term. When n is equal to 2, I do get this third term. And when n is equal to 3, I do get this term. So this is how we would represent cosine x as a Taylor series. Well, it's actually a Maclaurin series since it's centered at 0, but we can call it a Taylor series centered at 0. If we were to look at the different degree polynomials, we would see that the higher the degree went, the better the approximation is for cosine x. Looking at this graph, this blue graph right here is going to be the graph of y equals cosine x. And then our 0 degree polynomial was just the constant y equals 1. The second degree polynomial is a quadratic, and that's this graph right here that looks like this. It does a good job of approximating cosine up until a little bit past 1. And then our fourth degree Taylor polynomial would be this gold graph right here, and that one does an even better job of approximating the cosine curve. Remember, the blue graph is the cosine function. So as our degree of our polynomial gets bigger and bigger and bigger, this cosine function is closely being approximated by these curves for further and further distances. If we let n go off to infinity, then we would have the actual graph of the cosine function. So these polynomials converge to cosine as n goes off to infinity. We can deduce the behavior of the cosine function arbitrarily far away solely from knowing the values of the cosine and its derivatives at x equals 0. Now I'm going to give you some helpful information right now. Frequently you can get a power series for a function by manipulating a known series. And that's what we're going to focus on when we get into the next section. But I'm going to go ahead and give you the steps that we're going to use in section 10.9. The first thing you're going to do is you're going to substitute into a known series. You can also multiply or divide a series by a constant or a variable, and that will change your series. Another thing that you can do is add or subtract two series. You can also differentiate or integrate two series if you know what the series look for. So I'm going to give you some common series. And if you don't already have these on your series test sheet, you can go ahead and add these to them. If you printed out the copy of the series sheet that I have posted in Brightspace, it won't have all of these listed, but I think the one that I gave you in class probably does. So make sure all of these are included on your series sheet. I'm also going to give you the interval of convergence for these series. The first one we've already developed, the e to the x function. The second one is sine x, and this is going to converge for all real numbers as well. And we already did cosine x. The interval of convergence for sine and cosine and e are all negative infinity to infinity. Another one that you may need is tan inverse or arctan. It looks an awful lot like the sine function, but it doesn't have the factorial in the denominator. And this one's only going to converge from -1 to 1, including the endpoints. And I believe last time we also looked at this function. This is the geometric series where x is equal to r. That's just x to the n, or that converges from -1 to 1, not including the -1 and the 1. So pay attention to the parentheses and the brackets. The last one that I think you'll need for your homework is the natural log of 1 plus x. So this is going to be -1 raised to the n plus 1 times x to the n over n. This converges from -1 to 1, not including the -1, but including the 1. So these common series you can add to your series test sheet. You will also want to include the interval of convergence for each of these. I've written out what the series looks like, as well as what it looks like when it's expanded. You don't have to prove these anymore. You can use these now to manipulate series and find convergences of different series. Example 3, given that cosine x is equal to the series that it's equal to, find the Maclaurin series for the function x times cosine x. In order to work this problem, what we're going to do is we're going to start with the function x times cosine x. We're going to use the series representation for cosine x. And when you have a constant that's multiplied outside of a series, can you bring that constant into the argument of the series? Yes, you can, and that's what we're going to do. So we're going to rewrite this as the sum n equals 0 to infinity of -1 to the n x to the 2n divided by 2n factorial times x. Now x I could write as x over 1, which means it's going to go in the numerator. Now when you multiply with a common base, what are you going to do to the exponents here? We can combine these two terms. And that means that this series will be equal to the sum n equals 0 to infinity of -1 to the n, and x to the 2n times x to the first is going to be x to the 2n plus 1 divided by 2n factorial. The only thing multiplying that x times the cosine did was it gave us an extra x here in the argument of our series, and so I can multiply using properties of exponents, and that changes the power on x. In the next example, I want you to find the Maclaurin series for sine of x squared. We know what the series is for sine of x, so all we need to do is start with that series for sine of x and replace x with x squared. So we have the series that goes from n equals 0 to infinity of -1 to the n times x squared raised to a power of 2n plus 1 all over 2n plus 1 factorial. When you raise a power to a power, what do you do to the exponents? You multiply them, and that means you've got to distribute that 2 across there. So that means that this series representation is going to be the series that goes from 0 to infinity of -1 to the n, x raised to the 4n plus 2 all over 2n plus 1 factorial. And that would be our final answer here. So you see how you can take a known series and find the series of a similar function by manipulating the terms from the known series. And this is going to wrap up section 10.8.